In this video, I want to talk to you guys about the binomial distribution again. Just as a quick reminder, for something to satisfy being a binomial distribution, for x to be a binomial random variable, we need these three things to be true about the experiment. Each trial in the experiment is independent, so the outcome of one trial doesn't affect the probability of the outcomes of any of the other trials. And related to that is each trial has a fixed probability of success, so the probability of success is the same in each trial. And each trial has two outcomes, either a success or a failure. And we're going to do a few examples of binomial random variables and how to think about them now. So the problem we're going to be dealing with today has to do with a vote tallying company, and they want to be efficient, or more like lazy in some sense. So there was a population that voted between two candidates, A and B, and to save them time, they just want to take a sample of 5 votes, and they want to say, well, we'll count the most out of those, and whoever got the most in that sample we'll call the winner of the election. So that's our experiment there. They're going to draw 5 votes, and they're going to count how many voted for each candidate. So suppose that this election was a landslide. So 75% of the voters voted for A, and only 25% of the voters voted for B. And let's say there are no spoiled ballots or anything like that. Every vote is either an A or a B. So what is the probability that if they randomly select 5 votes, that the sample gives an incorrect conclusion? And let's assume that the population is quite large, so that if we do draw a ballot from our sample, the change in the probability for the next ballot being for a particular candidate is so negligible we can just count it as the same. So we're going to assume a very large population here. So my suggestion for you guys is pause the video now and see if you can answer this question, or at least set it up. First of all, think if indeed this scenario does satisfy a binomial random variable. First of all, what will be the random variable? What are we interested in counting? So pause the video and try this. At least try to set it up. And then when you're ready, you can unpause and watch the rest. All right. So first of all, we need to define what we're interested in counting, what can vary with some probability. That's a random variable. And we care about the number of votes. For, we can either say candidate A or candidate B, it doesn't matter. Let's do it for candidate B, since we want an incorrect conclusion, which means that candidate B will be the winner of the election. So let's count the number of votes for candidate A. We should be able to get a very similar answer if we counted the votes for candidate A instead of B, so there's no big deal there. So the whole idea is we're selecting 5 votes from our population of votes. So here are our 5 votes. And we know that for each vote, there's a 75% chance that they voted for A, and the rest, 1 minus 75%, so 25% chance they voted for B. And we're going to count this, since this is what we're interested in for a random variable, the number of votes for candidate B, we're going to count that as our success. So there's a 25% chance of success here. So what would be an incorrect conclusion? It would be that candidate B wins the election, which means that they must have got 3 or more votes. So an incorrect conclusion is candidate B gets 3 or more votes in our sample of 5 here. So we want to find what's the probability of that. So we want the probability that the number of votes that candidate B gets, which is a random variable, x, so I'm just calling it x, so I don't have to write that big long sentence. So that is, we want the probability that that is greater than or equal to 3. And remember, our formula for the binomial distribution calculates for exact numbers. So we'll just have to do it for each individual case. So for when the number of votes is 3, the number of votes for B is 4, and the number of votes for B is 5. So let's calculate these. So this is going to be, well, we have 5 votes in total, and we have 3 successes, so 5 choose 3. Or if you're familiar with NCR notation, this would be 5C3. Or if you like, just in terms of choosing, not choosing, this is 5 factorial over 3 factorial, 2 factorial. All of those things are the same thing. Anyway, 5 choose 3 times the probability of success, which is 25%, to the number of successes, which is 3, and the probability of failure to the number of failures. That is the probability that we have exactly 3 votes for candidate B, because that's what our formula gives us. We'll do the same thing for 4 and 5. So it is 5 choose 4, 0.25 to the 4, since we want 4 successes in this case, times 0.75 to the 1, since there's 1 failure if there's 4 successes. And finally, 5 choose 5, which is just 1, 0.25 to the 5, and 0.75 to the 0, if you like, but anything to the 0 besides 0 itself is 1, so we don't even have to write that down. So I would say pause the video and try and calculate this, and I will give the final answer in a second. Okay, if you did this correctly, you should get that this is indeed just over 10%, 0.10, say 35. So about 10.35%. So even in a landslide election where 75% of the candidates voted for candidate A, with this quote-unquote efficient method of just taking a sample of the votes, there's still a 10% chance that it will get the incorrect conclusion. And maybe, as a little exercise for you guys, let's do the same thing, but let's change the election so only, let's say, 55% of voters voted for candidate A. So again, what is the probability that in this case, where it's a more narrow election, what's the probability that B wins even though B shouldn't? So pause the video and try that yourself. Okay, now that we're back, if you did that, you should see that we get about 40, let's say 0.69% or 0.4069. So that's quite high. So you can see why taking small samples of votes like this gives incorrect conclusions lots of the time. Let's do one more example. Okay, in this example, let's say we're dealing with a class of 10 students, and the rule at this university is that if a student tests positive for COVID, then the whole class is canceled. So a professor decides that they want to give all their students in the class a test on the same day. And note that the false positive rate for the test is let's say about 10%, let's say equal to 10%, just to give ourselves a really nice firm number. So remember, the false positive rate that's the probability that if you don't have COVID, you'll still test positive. These tests aren't perfect. 10% of the time, if you're COVID free, you'll still test positive. So my question is, what's the probability that the class will be canceled if all of the students in the class don't have COVID? What's the probability that it'll still be canceled anyway? And then the second question is, what if the rule was changed to 2 or more students need to test positive in order for class to be canceled? What's the new probability that class will be canceled? So again, pause the video and see if you can figure this out. Okay, so first of all, this seems to be a binomial random variable problem. We're interested in the number of students that are going to test positive, so that's going to be a random variable. It's a number that changes as a probability of each outcome occurring. That's great. The test results are independent for each student. The probability of me testing positive does not affect the probability of the person next to me testing positive. There's only testing positive and not testing positive, so there's a success failure thing. So this satisfies the conditions to be a binomial random variable. This is great. So let's move on and let's actually calculate this. Okay, so a random variable we said was the number of students testing positive. And our probability of success, I like to use the letter P for that. Well, we know that each student has, if they are all COVID-free, each student has a 10% chance of testing positive. So 0.1, or I wrote it as 0.10, it doesn't really matter. Or you can write it as 1/10, doesn't matter at all. Okay, so we're interested in the probability that class will be canceled. So that means we're interested in the probability that the number of students testing positive is 1 or more. Now, you could, if you wanted to, naively calculate the probability that X is 1, the probability that 2 students test positive, all the way to the probability that 10 students, I'll write 9 and 10. 10 students test positive. You could do that, but you could imagine that is a lot of work. So maybe pause the video and see if you can come up with a better way or more efficient way of calculating this. Remember, probability has this property where the probability of all possible outcomes must sum to 100%, to 1. So we might be able to use that to help us figure this out. So pause the video and see if you can figure that out. Okay, so if we think about this, this is every case except for no students testing positive. So we can use that idea to say the probability that at least one student tests positive is just the complement of the probability that no students test positive. And if we think about it, Well, this is 100%. So this is the probability of all our outcomes added together. Probability that x equals 0 plus the probability that x equals 1, all the way to the probability that x equals 10. And if we subtract off the probability that x equals 0, we're left with what we want. So we can use that thinking. We could just start with everything and subtract off what we don't want, and we'll just have what's remaining. And this calculation is a lot easier. So let's go ahead and do this. So this is 1 minus, so we want 10, choose 0 here. And then the probability of success is 0, so I'll write a 0.1 to the 0. And the probability of failure, 1 minus p, is 0.9. There's a 90% chance that you don't test positive. And there are 10 students that don't test positive if 0 students test positive. Okay? So again, pause the video, see if you can calculate this on your calculator or by hand, and then come back and I will give you the answer. Okay, so you should get that this indeed calculates to 1 minus 0.3487, which is 0.6513, rounded to, say, 4 decimal places, so 65.13%. So even if no student has COVID with this rapid test with a 10% false positive rate, if everybody takes it, the probability that at least one student will test positive is about 65%. So you can see how doing lots of experiments with things that have decent false positive rates will give you, on average, at least one success. So that was A. And for B, well, we're changing it to 2 or more students, so we want the probability that x is greater than or equal to 2. So using the same reasoning that we did above, pause the video and see if you can indeed figure that out. Okay, so again, we could do the probability that x equals 2 plus the probability that x equals 3 plus the probability that x equals 4 all the way up to the probability that x equals 10. Or we can just start with everything and subtract off what we don't want, which is the probability that x equals 0 and the probability that x equals 1. So again, pause the video, see if you guys can indeed calculate this. I will leave the details of the calculation for you guys to check yourselves. But we know this answer here, that is that. So we just need to figure out this probability here. But that's okay. So pause the video and see indeed if you get the same answer that I do. Okay, so I calculated 0.2639. So the probability now that class gets canceled if the rule is, well, 2 or more students need to test positive, there's still over a quarter chance, over a 25% chance that class will indeed get canceled.